Right, x equal -2 plus minus square root of 19 over 2 are the root of the equations. So we write the equation as two factors. So the first one is that's the first factor. The second factor is plus 2 minus square root of 19 over 2 close. Next thing is we're expanding the two factors together. So we will have this one times that, that's x squared, and this one times this one here, so it's positive 2 minus square root of 19 over 2x, then plus 2 plus square root of 19 over 2x, sorry, yeah, plus, and that last one multiplying the constants together. So we will have, I'll just leave it in brackets now, okay, and then simplify now. So it's x squared, those two, the common factor is, sorry, the common denominator is 4, so basically 2 plus 2 is 4, square root of 19 minus square root of 19 plus square root of 19, that will simplify, so you will end up with 4 over 2x plus, and then expanding this one here, so you can use it, use the calculator to do it, and the answer is 15 over 4 equals 0. Then simplify, you'll end up with x squared plus 2x plus 15 over 4 equals 0. And then if that's divide by 4, so if I multiply all the equation by 4, I end up with 4x squared plus 8x plus 15 equals 0. So A is 4, B is 8, and C is 15. It's 15. You don't have to write what the value of A, B, and C, because they just start you to equation of in the form of ax squared plus bx plus c, and that's your final answer. Next question. You've got two complex numbers. I've only shown the diagram, so the questions are on the, you've got this with the V1 first. So V is, the real part is 2, and the imaginary is -1, so it's -I. And the U is, the real part is 1, and the imaginary is -2i. And they're asking you to find the value of uv, so u times v. So I would multiply them together first, so it's 2 minus I times 1 minus 2i, and if you expand the brackets you will get -5i, and then you mark it on the, so that's uv value. Okay, it's a cubic equations. So the cubic equations will have 3 factors. I've already got one of the factors in here, which is quadratic, so that's mean 2 factors, so I need to find the third factor. To find the third factor, that I will do is x, I'll write this cubic, so the quadratic one as one of the factors. Then I'll have to figure out that third factor. Looking at the first term and the last term of my cubic equations, I can figure out this factor here. X squared, you figure out what terms you multiplied by x squared, give me 4x cubed, which is 4x. Then what term you multiplied by +2 to give me -2, which is -4. Then you would expand normally from here, so it's 4x cubed plus 12x squared plus 8x minus x squared minus 3x minus 2. Then collecting the like terms, got 4x cubed and 12x squared minus 1x squared. I've got it's 11x squared, so it's positive 11x squared. Then I've got 8x and negative 3x, that give me positive 5x minus 2. So a and b, so a is 11 because it's the coefficient of x squared, and b is 5 is the coefficient of x. Because it says find a and b, so if you stopped in here that's not enough, so you need to say what's the value of a and what's the value of b. Next question. Okay, next questions will give you two complex numbers, w and z, and they will ask you to prove the argument of wz is equal pi over 4. Because it's wz, that means you have to multiply w and z first. So you find the values of w and z just by multiplying. You can use your graphic calculators to do that, or you expand normally. So the value for that is 17 plus 17i. And to find the argument, which is tan inverse, so this basically, if you think about it, 17 positive for the real, and that's 17i for the imaginary. So your factor, which is w z, is basically here. You need to find this theta here. And to find this theta, I've got the opposite of the theta, which is 17. The adjacent of the theta is 17. So tan inverse to 17 over 17 give me pi over 4. So the argument of wz is pi over 4. The next question, z is a complex number. Ki and w lies on the locus of arguments pi over 4. So this one here too is pi over 3. This one here to understand it, you must draw it. That's the easiest way to figure out. Now I'll draw the argument first. So you've got the complex numbers. The first one is ki. Ki is just imaginary, so somewhere here. Don't worry about the value of k, it's just the imaginary part. So that's ki. Now the focus, the length of k equal the length, the w lies on the argument z pi over 3, means this one here is pi over 3. W lies here, so it could be here, it doesn't matter, but W lies on the focus of the pi over 3, the argument of pi over 3, so it's on this line in here. Now the next bit says length of z equal the length of W, so that's mean this one here, the length of this one, which is, let's say, call it, which is at the moment is obviously it's k, because it doesn't matter, and this length here will be k as well, because they are equal. You need to find the length of z minus w. So this one here is z minus w. This is the length of z minus w. Now you've got a non-right angle triangle. You've got two sides in here, and you need to find the third one. Now this is pi over 3, so obviously this angle here will be 30 degrees, because everything needs to ends up to 90. Pi over 3 is 60, so this is 30. Now I've got an angle opposite to the unknown side. I've got two known sides, so that means I can use the cosine rule for the non-right angle triangle. So the cosine rule is a squared equal b squared plus c squared minus 2bc cosine a. Now a squared is w, length of z minus w square. B squared is k squared plus another k squared, because the two lengths are equal. minus 2k squared, because k times k is k squared, over cosine 30. Now you can work with radius. I just like to work with degrees all the time, so that's why I converted to degrees. Now solving this one here, 2k squared minus 2k squared cosine 30. Cosine 30, you can find out the answer for the cosine 30. I'm not finding it out now because I always try to use in the calculator, I use the answer button, so I'd avoid rounding. So I'll end up with 2. If I do 2k squared minus 2 times that, I will end up with 0.268k squared. Okay, that you can find it in the calculator. Just 2 minus 2 times cosine 30. Make sure that your calculator mode is in degrees, and then square root both sides. I'll end up with 0.518k, and that's your answer, the length. Next one, find the modules and argument of z, which is 1 minus I. The length of z, the modules mean the length of z, which is square the imaginary part plus square the real part, so basically 1 plus 1 equals square root of 2. Now the argument of that is tan inverse 2 imaginary opposite over adjacent, so will be imaginary over real, and imaginary is negative 1 over the real is 1, which that give me pi over 4. So that's mean z is square root modular cis pi over 4. It's quite simple. Alright, so the first step, I would square root both sides. So you end up with 1 over positive negative 2. Then rearrange to having z on one side of the equation. You will end up with either negative 2 minus negative 2, or you end up with 1 over z squared positive 2 minus 2. This one will give you 0. So that's when ignore. You'll ignore the solution. Then you will only focus on this one here. Rearrange. You will end up with 1 over negative 4 equal z squared. Now square root both sides. You'll end up with 1 over 2i, because it has a negative, so square root of negative 1 is I. So that's why positive negative half I. So that's your final answer. Okay, you've got the cubic equations in here. You've been given a cubic equations. We have given one of the root is 2 plus 3i as a root. So it's definitely that's mean is 2 minus 3i is another root. So that's your first step. You would say 2 minus 3i is a root. That's your first step. Then you would rewrite those as factors. So z minus 2 minus 3i. And the other factor is z minus 2 plus 3i. Expanding this one here and simplify, you will end up with z squared minus 4z plus 13, which is, that's what's being given in here, which is, so you will say then that means z squared minus 4z plus 13 is a factor, which is, that's what you want to be proven. Okay, so that's the starting point. If you started with the starting point correctly, then it's quite straightforward. You just expand. Okay, now show some of the roots. So first of all, the first step is you need to find the roots. Find the roots, you're going to use the root theory. So z to the power of 3 equal k3. Now to find the three roots, so this one cubic root, so that's mean the to the power of 3, so that means it has 3 different roots. To find the 3 different roots, we're going to use, you take the cubic roots first for k, which is k, then cis. Now the angle in here, or the theta, the original theta is 0, because the imaginary part is 0, so 0 over anything is 0, so that's why the theta is 0. So 0 plus 2 pi n over 3. This n, you're going to use 3 different values of n, because we want 3 different roots. You can use the graphic calculator and you go to tables. It's the same way that I've showed you, or you can just try. I'm going to use n is equal to 0, n is equal to -1, n is equal to 1. Now substituting n, the 3 n's in here, you will find the 3 roots. The first root is k, the second root is k cis 2 pi over 3, and the third root k cis -2 pi over 3. Now you're going to rewrite each one of those roots as a rectangular form. So the first one in rectangular is just k. The second root in rectangular form is -k over 2 plus 0.87 k. The third root, it's k over 2 minus 0.87 k. Now the sum means you're adding them all together. So add all the roots together. Okay, that's negative as well. Sorry. Okay, now adding them all together, -k over 2, -k over 2, that give me -k. With that positive k will simplify, so I'll simplify those two. Positive, negative, that simplifies, so that's 0, and that's what's, so it's proven. The sum of all the roots is 0. Now, you've got the two equations, both of them value equal to y, and they have two distinguished solutions. You need to find the value of k. So the first thing, both of them equal to y, so I make both of them equal to each other, so, and rearrange and solve. Rearrange. Positive 6x, positive x, that's positive 7x minus k equals 0. Now I've got a quadratic, a cubic equation. So because it's cubic equation, and it has two distinguished solutions, that means one of the solution is repeated. So I would rewrite that as x minus a all square and x minus b equals 0. This is repeated and this is different, so that's why I end up with two distinguished solutions. Now if I expand everything in here, the first one I expanded as x squared minus 2ax plus a squared, and that's x minus b equals 0. Now keep expanding. Plus a square x minus a square b equals 0. Now I would like to compare this one here with that equation. So all the coefficient of x squared should give me -5, all the coefficient of x should give me 7, and all the constants should give me k. And that's why I will end up with three different equations. I've got a squared times b is equal to -k. That's negative, and I end up with -b minus 2a equal -5, and I will end up with 2ab plus a squared equals 7. Now I've got three different equations and three different unknown if you think about it. So I could use those two equations here to find the values of a and b, all right? And then how would you work this one out is this, rearrange it in terms of b. So I would do that one. I would say, just going to continue in this one here because there's not enough space. I'll have 2a equal 5 minus b, just rearranging, and then we'll end up with b equal 5 minus 2a. From this one here, then I will take this equation substituted in the other equation, the one is equal to 7, just trying to solve them simultaneously. Solving the whole thing, I'm not going to solve the whole thing, you can solve it yourself, and then you will end up with a equal 1 or a equals 7 over 3 by solving this equation. So again, I took the first equation here, rearranged it, written it in terms of b, substituting this b in this second equation, rearrange the solve, I end up with a and b. Now I took a and b, substituted back into that first equation, I'll end up with 2 b's. So that means b is equal to 3 or b is equal to 1 over 3. And because you've got now the 2 b's, now the k is a squared plus b. So that means k is equal either 7 over 3 squared times 1 over 3 or k equal 1 times 3. And that gives me 3, and that's give me 49 over, that's 9, so it's 29 times that, 27. So those are the two values of b. Next, that's the last questions. So A from this question is another achieved questions. Is basically you've got those two complex number, not complex, but square root of 3. You need to write it in this format, a plus b square root of c. That's mean you will treat it as a complex number, so you will multiply it by the conjugate of the denominator. Okay, then after multiplication you'll end up with 2 plus square root of 3 plus 2 square root of 3 plus 3 over 4 minus a 3, end up with 5 plus 3 square root of 3 after simplifying. Now next questions, you've got the argument of b is 5 pi over 8, the argument of w is pi over 3, right? The argument of v times w and v over w. Remember when we multiply in the arguments formats, then you will add the angles, and when you divide you minus the angles. So it's basically for VW you will add the angles. It's 5 pi over 8 plus pi over 7. That is giving me 43 pi over 56. That's it. And V over W you minus, so it's 5 pi over 8 minus pi over 7, and that's giving me 27 pi over 56. So that's your final answer. Right, for this one here you've got show z is an I is equal to I is a root of this. First of all you have to show it's a root. So that's your first step. To show it's a root you will have to substitute in the equation and you should end up with 0. So you will have I to the power of 4 plus I to the power of 3 plus I minus 1, and that's I, so I to the power of 4 is 1 minus I plus I minus 1, and if you simplify everything that give me 0, so I is a root. Now because it's, find the other roots, because I is a root and this equation has no imaginary, so that's mean negative I is a root as well, so negative I is another root. Now you need a third root. You need another 2 roots because z to the power of 4. We already have 2 roots now. To write that, you will rewrite those roots as factors, expand. So you'll end up with this. Now if I divide the main equation by that, so it's a long division, just divide it, z square first, minus then times by z, because zq first, next, minus that's positive, sorry, positive, minus 1, and then if I do minus 1, minus, I get that to 0. That's minus positive z square minus, so it's minus z square, that's minus, and that's minus, so that gives me plus, so that's end up with 0. So that means z square plus z minus 1 is the other root. So the roots are I, negative I, and z square plus z minus 1 is the third root. So that's fourth, that's give me another 2 roots. And if you solve this using your graphic calculators or just using the quadratic formula, you will end up with I, negative I, and the other 2 roots are negative 1 plus square root of 5 over 2, or negative 1 minus square root of 5 over 2. You can find those two by solving this equation here, either using the quadratic formula or using your graphic calculators, doesn't matter. So you've got 4 different roots to the power of 4. Right, next one, z is a complex number, then z conjugate is another complex number, is a complex conjugate. If u and v are complex numbers, prove that u plus v multiplied by the conjugate of u plus the conjugate of v the same as the length square of u and v. So I'll start with this side of the equation first. So I will assume u is a plus bi. So that's mean u conjugate will be a minus bi. The v is c plus di. So the v conjugate will be c minus di. Now I will find this one here. So a plus bi plus c plus di multiply by the conjugates plus c minus di. Now expand and simplify, so I'll end up with a square plus 2ac. I'm just expanding, a plus bi minus a di is a bit confusing because there's so many letters. It's just you have to be very careful when you expand it because it's so easy to make mistakes with signs. I think that's the hard bit about the question. It's not the way of solving the question. That's a, yeah, plus bi plus bd plus a di plus cdi plus db plus d square. So now simplify everything in here. There is lots of terms that you will cancel out. I'm just going to cancel them in the read. So abi negative with positive abi, negative adi with positive adi, this one here, and you've got negative c di. I think all the i's will go with negative positive c di and another negative with that one, so that didn't have an a, sorry, and I think that's it. Yeah, I can't find anything else. Hopefully I'm right. Okay, and then you simplify, you'll end up with this only. Plus c squared plus b squared plus 2bd plus di. Yep. Now, so this is what I got from this. Now I'm going to solve this one here. Okay, so I'm going to start with the u plus b length. So the length is square root everything square with a plus c square plus b plus d square. Okay, so now if I solve it out, that's d square. Sorry, that's not di, that's d square. Yeah, that's the term, that's d square. And positive bd, positive 2b, yeah, just checking because it's quite easy to make mistakes. Okay, so squared with that square will eliminate the square root, so you'll end up with a plus c square plus b plus d square. Now if you expand, rearrange, simplify, you will end up with a square plus 2ac plus c square plus b square plus 2bd plus d square, and it's the same as this one here, so you say proven. So you can see I've just, the hard bit in here is just the expanding, and make sure that you're doing the signs correct. It's quite straight, otherwise it's quite straightforward. Right. Alpha and beta are the root of bz squared plus az minus 1, which means that adding the two factors give me a, and multiplying the two factors should give me -1 times b, which is negative b. So a plus b, beta, is a, and alpha times beta is negative b. Now rewrite it as an equation, as factors, sorry, not roots. So alpha and z minus beta is equal to 0. Expand, you will end up with negative alpha minus beta plus, sorry, beta z, and plus alpha beta equals 0. Okay, now alpha plus beta in this case is a, so I'm going to rewrite it az. Now alpha times beta is negative b, so it's negative b equals 0. Yeah. Now this one here has a b square as a common factor. This one, as a coefficient of z square. This one doesn't. Okay, so to change it to that, I will divide everything by b. The reason is, well, this is -1. Can you see how is the last constant is -1? This one is b in this case. So I will divide everything by b just to get it similar to that equation. -1 equals 0. So from here, alpha and beta, it's -1 over b, and alpha plus beta is a over b. Okay, so that's minus, sorry. Yeah. Okay. Now, for that one here, then I will take the other one. Can you see it's 1 over alpha and 1 over beta? So I'm going to take those, write them as factors. Now expand, simplify, I will end up with Now, alpha and b is negative 1 over b. Okay, so 1 over alpha and b. So I'm going to take each term by itself. So this one here is similar. So if I substitute instead of alpha times beta, negative 1 over b, I end up this term will give me negative b. Now this term here, I'll have first to write it as one fraction. So to write it as one fraction is beta plus alpha over alpha times beta, just finding the common denominators. Now alpha plus beta, I've got it already a in here. And alpha times beta, it's alpha plus beta here is a over b, alpha of a over b, and alpha times beta is negative 1 over b. Rearrange that and simplify, you will end up with negative a. So my final is z squared minus a z minus b equals 0. And that's the same as the given equation. So you have proven. Those are factors. 1 over alpha and 1 over beta are the factors of these. Because when you multiply together, simplify, resubstitute, you'll end up with this equation.